And we're going to have our first panel come up. So I'm going to ask our panelists for our EECS data centers and the cloud panel just to come to the front stage for me, please, so that we can get started. Okay, so we have 5 wonderful panelists. Can you give a round of applause for them, please? Now, I'm going to let them introduce themselves, but for you panelists, I just want this to be just a general discussion amongst ourselves here. I have some prep questions just to kind of get the conversation going, and then we'll go into a Q&A with the audience. Sound good? So with that being said, Rob, we have you first. Would you like to introduce yourself? Oh, is it on? Let me turn it on for you. Sorry.
Hello? Can everybody hear me?
Yep.
All right, perfect.
Bring it forward.
Okay, yeah, I've never seen my face that big before, so I apologize for that. My name is Rob Wong. I'm a software manager at AMD with the cloud and virtualization team. I've been with AMD for 5 years. I've also been 10 years in the fintech industry prior to AMD, but my background is computer engineering at the University of Waterloo.
Woo! Okay, there we go.
Oh, that's me. All right. Hello, everyone. Probably many of you know me because you were in my class or just see me around the Lassonde building. My name is Hamzeh Khazaei. I'm an associate professor in the Department of Electrical Engineering and Computer Science Department. And I just tried to have everything on this slide. On the right, you see the lab member that I work with, the graduate students. And by the way of that, I'm going to tell you the research that we do. The cloud computing is at the heart of it, and we are working with the betterment of cloud systems, mainly performance, availability, and the reliability of those systems. I also teach system courses in the department, the operating system, distributed system course, performance evaluation of systems, and also we are going to have a new course, machine learning system, hopefully next year, that is going to be offered for the 4th year undergrad student. And I'm really happy to be here, and thank you, Kodrin, and also the other people here for this amazing event.
Okay, I guess I'm next. My name's Dustin, Senior Director of Analog Mixed Signal Circuit Design at Alphawave Semi. Alphawave is a company that was built on building hardware specifically for data centers, which is a part of the cloud, which is why I'm up here. Software questions will probably go to my colleagues, but anything about hardware, I can step in. I'm also here representing IEEE Toronto. I'm the chair of the IEEE Toronto section. So if people have questions about IEEE, what that is and how you can get involved, either while you're a student or after you graduate, come talk to me over at the Alphawave table. I'd love to hear from you. Thank you.
I guess I'll go next. Good afternoon, everyone. My name is Marija Mijalkovic. I'm an account technical leader with IBM Canada. I've been with IBM almost 30 years. In the role that I am now, I work with a very large Canadian financial institution, and I help them adopt all of our IBM offerings, so that's both software, infrastructure, and cloud, and help align our strategy with their goals and objectives. Previous to that, I spent about 25 years in our infrastructure business, and so in infrastructure, we did a lot of business in data centers and of course, the transition to cloud. And I'm really looking forward to this discussion today, and I'll hand it over to my colleague, Kosta.
Thanks, Marija. I am Kosta Makropoulos. I, too, also work for IBM Canada. Fun fact, I replaced Marija at one of her last positions at IBM. So I, too, have been with IBM for 25 plus years. I am currently the Canadian market subject matter expert for storage for data resilience. I spend roughly half my time in data centers, whether they're IBM data centers, customer, client data centers. And yeah, I basically help clients build, deploy data center infrastructure. I'm more on the infrastructure side, so hardware, yes. But I also deal with storage infrastructure and software that's required for that. So my primary responsibility is what we call data resilience. Some of you will recognize that as cyber. So I have the pleasure of, unfortunately, helping clients try to respond and recover in the event of a cyber attack.
Awesome. What I'm going to do really quickly, I'm just going to take these mics out of their stands. So it's a little easier for you guys just to pass the mic around. Okay, let's get started. So I will be your moderator for today. For those of you who don't know, my name is Gordon Little. I'm an electrical engineering student here at York University. That being said, I think it's good to start off with some definitions. A lot of people hear cloud being all hand-wavy, you know, the cloud this and data centers that, but what exactly is the cloud? Would anyone like to take a crack at that? What is the cloud? How would you define the cloud?
Okay. Actually, when I was doing my PhD research, it was like around 2009, and as you know, cloud was kind of the inception of cloud was around that time, 2008 and 2009. And one of the things that I needed to come up with was the definition of cloud computing, because there was no kind of standard definition at the time. I have my definition in that thesis that basically cloud computing is a new paradigm of computing in which you can access a huge amount of resources in terms of infrastructure, software, or platform on demand and in a kind of elastic way. And that was kind of my formal definition of cloud computing. Of course, from that time up until now, we have had a couple of iterations of different cloud systems. But the definition actually is pretty much the same, and you can have access to these resources on demand, and has a model of pay as you go, which the ideal, the promise of cloud was that you pay for whatever you use. We haven't realized that initially, but we're moving toward that to really you pay for what you exactly use. The latest paradigm is serverless computing, which gets you close to that notion that you as a customer, you are not worried about the complexity of cloud. You use it as a service paradigm, and also you pay only for the resource that you really use.
Oh, yeah, I could probably add to that too. So, no, my team at AMD, when we first started, we were trying to separate shared GPU amongst multiple people. So who knows what a GPU is here in the crowd? All right, awesome. I don't have to explain it, so that makes it easier for me. So back in 2019, 2020, COVID-19 hit. And before that, a lot of people would be in the office. They would have this incredible workstation at their desk, and they'd be doing, I don't know, next Pixar movie, maybe doing AutoCAD, some type of workload that we would need a GPU to accelerate it. But pandemic hit, everyone had to go back home, and you don't have access to it anymore. So this is where our team used our solution, where we take the GPU into the cloud, such as Microsoft Azure, and we use our software stack to be able to split one GPU amongst multiple users, such that employees who are working at home can now work on these workloads remotely with the full power of the GPU they would have at their cubicle at work. So, so that's one use case that we have in the cloud perspective. So.
Do you want to go or you? So I just wanted to, and the kind of the example and the professor's comments were kind of spot on, but at IBM, we're very passionate about that concept of a cloud and, again, comparing it to a data center, right? So because they're not two choices in our view, I would think, and one is almost a requirement for the other, right? So a data center is a building with lots of compute and storage and networking infrastructure, and you absolutely need a data center to support a cloud. But a cloud is really just a way, it's a model, it's a way for you to consume infrastructure, applications, services, resources, right? And so you know, at IBM, cloud is not a place, it's a way you consume, and you can absolutely build a cloud and have a cloud model anywhere. And that's why we're very, you know, as a business, we are focused on two themes of AI and hybrid cloud, and hybrid, that notion of a hybrid cloud, that it's not a place or a destination or somewhere you go. It's a model of how you consume software, applications, resources, different types of technology, and you can really build it anywhere. It's how you build it, how you consume it, the technologies that you use, the democratization of that layer in between the physical hardware and the software. That is really what we refer to cloud. And I know I've probably maybe confused it a little bit, but just this notion that it's not somebody else's hardware. You can, and a lot of clients do this today with technology that from a company known as Red Hat, and I'm sure you've heard of. But you know, if you build applications based on, you know, containers, they make them very easy to move, and then you can, that is what true cloud is to us, right? The notion of being able to move software and applications anywhere on any hardware, doesn't matter what building it sits in or the logo on the building outside. So.
Okay, thank you very much for the definitions. Now, I think you touched on something very important there, which is you can't have one without the other. It just almost makes no sense, right? With that being said, could we talk a little bit about like where do data centers and cloud meet? Like how do they meet? How do they interact with each other? What is the, how would you describe the process in which you have a cloud service hosted in a data center? Who'd like to take that up?
So the data center, actually, we have had data centers since Google, like 1995. But the only thing is that the only, like this big company, they had all these resources, and it was only accessible to them. And then cloud, as I said, is a computing paradigm that actually democratizes all these resources so that everybody can use them. Like, I mean, from you, a student, everybody can use by the way of the cloud paradigm. So it's no longer like only accessible to the big firm, and everybody can use these resources and does the job that they want. Data center is something like more, as I said, it's the kind of old concept. As long as we have large amount of resources in terms of computation, storage, networking, and all other capabilities, you can just look at that as a kind of the resource. But the cloud, as I said, is this enabling everyone to use that. And actually, the two main enablers for that, one is virtualization, that we got that in a kind of very stable version of a virtualization, and also a kind of very stable connection. With these two, we were able to just make sure that everyone can access the cloud. Also, just to put it a little bit of perspective, initially when we had the cloud, people would say, many people say that probably cloud is not going to fly, mainly because of the availability and also the security concerns. Because how come a company, for example, wants to put their data on someone else's computer? But as we know, that wasn't the story, and cloud is like pretty much everywhere. And when you are talking about distributed system, pretty much you are talking about cloud. At least part of that system is going to be on cloud.
I guess I could also add to it too. Let's say like at my old company, back then we would have like these file servers that would store all the files across the entire company, but they would buy all these equipments and they would house it in a building somewhere, they would hire a team, and then maintaining that would be really, really expensive. And then when AWS came along and offered these services to all these companies, it's like, well, okay, wait, we don't have to like buy this equipment. We could just rent it out from Amazon. And it just became cheaper. You don't have to hire as many people to maintain this. You don't have to care about the hardware goes down. AWS would guarantee that for you. So a lot of businesses would be like, okay, you know what? It's just much easier to just rent this from Amazon instead of like maintaining ourselves. It's like, do you buy a car or you call an Uber? So if you buy a car, you have to pay your insurance, you have to fix it, you have to like make sure that you don't get into a crash versus like pull out your app on Uber, call it, get to your destination. So that's one way I like to look at it from the data center versus like a cloud way where Uber is like the cloud and owning a car is like the data center.
I think a lot of good points were brought up here. Again, to Maria's point, a cloud is still a data center under the covers. So there is some building somewhere with compute, storage, networking resources. I think the advent of technologies like virtualization, which, by the way, if you didn't know, has been around since the late 1960s on mainframe computers back in the day. And better networking is a key point. Being able to access these commodity resources remotely and still maintain application latency and performance. So security is also a part of it. Before, you would have to own your own gear. Whether your utilization rate was 10% or 80%, you amortize the entire purchase, whereas now you pay for essentially what you use. But under the covers, it's still the same technology that's being used in terms of infrastructure. It's that software layer that has allowed these companies to be able to partition out the environments, provide them either as a service or bare metal, and be able to allow you to consume what you want, when you want it, scale up or down when you want it. So it's that flexibility.
And just adding to that point, I mean, every cloud is a data center, right? Like you need a data center to be able to build a cloud, but when you layer on those capabilities of provisioning and automation, it's really, the tons and tons of automation that goes in delivering cloud capabilities. When you add the software that delivers resiliency, right? You spoke about resiliency. When you add the capabilities that allow you to scale, that deliver scalability, the high availability, when you add all of those pieces on top of a data center, on top of the physical infrastructure, that's what turns it into a cloud. And that's why you'll see a lot of large organizations, they'll leverage public clouds and other people's clouds, but they'll also build clouds out of their own data centers that they have within their four walls. So it's again, more of a computing model versus a different, something different.
Okay, just kind of build on to that. So I know, Kosta, you mentioned especially improving in networking, even down to the bare metal. And I want to give Dustin the chance to kind of talk about the connectivity here, because a lot of people don't really think about the actual hardware as much as they should. So Dustin, would you like to talk about it a little bit?
Sure, yeah, thank you. So I think that the important point that I want to get across is that everything that the cloud enables for us, if there's a lot of engineers in the room here, I think if you go start a business that's doing technology, or you work for a startup, it doesn't have to be you starting it. If you're doing technical stuff, you're using a lot of computer power now in 2025, whatever it is, whether you're electrical engineer designing circuits, whether you're designing software, mechanical engineer, you're going to be running simulations, you're going to be doing advanced things with computers that will need a lot of compute power, probably. It's not practical when you're starting a company to get all of that compute power and set it up in your office, like my colleagues were saying. But it's still a lot of data that you now need to get to that computing power, which is in the cloud, which means in a data center, in multiple data centers spread all over the place. getting all that data to and from the cloud is a huge challenge, and it seems like it's only going to get worse. If you believe like I do that in future years, you'll be doing more complicated things with more data. We just need to squeeze more and more data through the existing fiber that runs from here to the data centers where it's getting to. That's what Alphawave's been involved in. That's what excites me about the future of circuit design, and all of this networking equipment needs to get so much faster and able to consume more data without overheating the planet while it's doing it. There's a lot of challenges there, and I think it's an exciting opportunity.
Awesome, thank you. You guys are bringing up a good point with respect to data centers are everywhere, right? So that kind of brings me to another question. Like, how do you think about the compute systems? How are these workloads balanced, right? How are they allotted across the different servers and such? How does that work?
I don't know. Can you repeat? I don't know if we caught the question.
I'm so sorry. Let me repeat the question. The question is, how is the workloads for the cloud allotted across different data centers? How do we balance the compute? How does that work?
So the question is like, if a person has a workload to run, how does that get distributed across multiple centers? So I'm not an expert in this, but I know there's like balancing about how the workload goes across. Oh, maybe you can talk.
No, go for it.
Yeah, I mean, like even for one example that we have within our use case is that within one server, we would have 6 GPUs, and we may allocate the workload across all those GPUs, or we may say like, okay, this person is just going to, these 5 people want to use the single GPU, and we just give them equal time slices so that everyone gets a little bit of everything. So it really depends on what you're trying to do, whether it's you're training the next largest LLM, where if you're just trying to even play a game in the cloud, there's different ways and methodologies to get that across.
I think if you were to look at compute, everybody's got a laptop at this point, right? You have a finite amount of resource on that laptop, CPU, memory, disk, network, whatever it is, and you want to run an application. You will quickly find the limits of that single instance. So what did we do? We added a second laptop, a third laptop, a fourth laptop to combine resources. And I think from an application standpoint, how you can spread these workloads around, there are things called load balancers, where you could say, you know, once this first laptop, or in case of a data center, this server or set of servers reaches its capacity or its performance limitation, start moving that workload across with these load balancers to say, you go over here, you go over there, you go over there, so we can basically structure the environment so that you don't have a single hotspot. You're spreading out the workload across all the members. That's server clustering as well, storage clustering, networking, all of that intertwined so that you're not creating a hotspot. And to the point earlier about how much data is growing and how much we need to bring into the cloud and pull back from the cloud, I think it's really important to understand that you know, you're constantly chasing a bottleneck when it comes to data centers or cloud. That bottleneck today could be CPU, it could be GPU. That bottle tomorrow could be network. For years, it was storage. So we're constantly, as an industry, looking to innovate and try to find what's that next bottleneck going to be and how can I get ahead of it. So that when we're spreading applications across all these servers, whether they're in one data center or multiple data centers, that we're not going to be limiting our growth and our scalability.
And I'll just add a couple of points. I mean, that's a classic problem that has existed in computing for a very long time, right? And so you know, folks have been doing high-performance computing for a very long time. It's a very similar problem, right? You've got a bunch of infrastructure. You'd like to leverage it most efficiently as possible to solve your problem. And so I think, you know, in the cloud space and in this new AI space, folks have looked to some of the great work that all of the people have done in high-performance computing and HPC to you know, do distributed computing and to, you know, train. I mean, this is, you know, so the HPC folks have been doing it, and it's like the hottest topic of today, you know, training these LLMs with massive data centers. And so those parallelization initiatives and distributed computing, I think, is where a lot of this magic lies. And so I think it'll continue to be an area of deep interest. So.
Okay, thank you very much. Oh, would you like to go, Professor? Go ahead.
Yeah, your question actually is really open about the workload. But one big question would be that what is the current workload that we have on data center? And I can tell you that pretty much like 80% or about that of the new data centers usually are the ML workload for the training purposes and also for the serving. And actually this is like the current challenge and the hot topic in the workload on cloud, how we can manage to run all this workload, specifically that this type of workload needs a specific hardware. We call them in general like the accelerator, could be GPU, TPU, or any other kind of accelerator. And because we don't have too many of them, that's why they are very expensive nowadays to buy and also to establish a data center. And you hear every day, for example, OpenAI are building like this big data center mainly for AI, and also Tesla or all other companies, Meta, Google, everyone, actually building new data centers, the new generation of data center, to just be able to tame this high workload that right now we have. And in terms of distribution, as said, we have lots of sophisticated algorithm how we can actually manage the workload. But usually in cloud, we have something we call horizontal scalability, which is something against the vertical scalability. All time when you wanted to handle a like heavier workload, you used to buy a more expensive machine, right? With more RAM, with more CPU, something like that. But on cloud, we have this horizontal scalability, which is, you can think of as like townhouse versus high-rise building. In terms of townhouse, you can build as much as you have land, or basically you have money. So we just want to distribute the workload on multiple machines as opposed to one machine, and then we can increase the number of machines, which basically are virtual machines, or decrease it at the time that you want. So that basically is the big promise of cloud, that you only pay for that high traffic, and when you don't need it, you just shrink back to the like a normal workload that you have during your operation. I hope that was a kind of good context to the question of the workload.
Yes, you actually kind of went into the next topic, which I wanted to kind of briefly just touch on, which was like the next generation of workloads. A lot of people talk about AI, lots of other accelerators, as you mentioned before, as well as the massive amount of data that companies like Dustin's company will have to process through all of that. Is there anything you guys want to touch on really quickly with respect to the next set of workloads to pay attention to?
I mean, as we look towards the future, I mean, the problems and issues are really clear because they're all in the news, right? So these data centers will require massive amounts of energy, and because the device of the day are GPUs, and they consume a lot of energy, and so these are some really big problems that will be left to you and your generation to solve. And so providing the energy for those data centers, providing the cooling for those data centers, right? So there's the stories of towns being drained of their water systems, right, to support these data centers are these are some of the challenges. The investments, I mean, you can read about this in the news of big companies that they're reinvigorating old nuclear stations, right, because they want to be able to provide nuclear power to support the data centers. What does that mean, even from a Canadian business perspective, our opportunities for investment in data centers, and I think even the government, what they're looking at, because, I mean, we would provide a great way to cool data centers by virtue of our climate. And so these are the opportunities. And then as engineers, you know, and especially at IBM, we're always focused on, let's look at things from a different approach, right? So what are the devices? What is the chip technology, the semiconductor innovation alternatives that we can bring to the table? What about devices that don't consume as much power? Neuromorphic computing, if you get a chance, read up on that type of technology, which uses way less power. It's you know, a different architecture from a traditional computer that's kind of separates CPU and memory. It's very parallel to an LLM, and so when you put an LLM on top of a neuromorphic chip, it gives you some really interesting results. So those are the opportunities to you know, find out how we can accomplish the task of training these really large models with smaller models, with devices that consume less power, and even looking at the models themselves and innovating to make the models smaller so they use less power.
Thanks. I think as I was listening to the answer, it's complicated to balance workloads, and I was trying to think of a way to present it to a bunch of students that are watching this. I think if the next time you make a request to ChatGPT, most of us don't think about what happens. We put in the question, we get a good answer, hopefully most of the time, not always. But when you make that request, spend a bit of time thinking about where that is going, and if you had a choice, if you could be involved, where would you want the work to go? Would you want it to go to the data center that's closest to your house? That makes geographic sense. What if there's a data center a little bit further away but with lower workloads where you might get the answer faster? Would you rather that we direct the traffic that way? What if you had the option to send it even a little bit further where the energy cost either in dollars or to damage to the planet is lower? Would you be willing to wait a little bit longer for that? What if that place was in China and you have concerns about the security there? There's a lot of different factors that go into managing workloads that we never get to see anything about, but there's opportunity. Those questions that I'm asking, that I'm wondering, are the same things that someone is working to solve, and whoever can solve it better in the future will have success in that industry. And I think there's an opportunity to get involved and figure out how this needs to be managed, because it's one of those problems that's just going to get worse as more and more data comes flooding into the cloud.
All right, thank you very much. I do have one more question before we go into a bit of Q&A. So what skills or areas of knowledge would you encourage students to start building today if they are interested in this broad field? You can speak to whatever specific vertical you would like.
Well, actually, I have this suggestion for my student in my classes, so now it's a good opportunity to share that with everyone here. I think right now, every student that is graduating should be the best at using these AI tools, the Gen AI in particular. So I just don't understand if you get the idea in some classes that, for example, the teacher says that you shouldn't use these tools because it's pretty much become like internet, right? It's something like that. You say you don't use internet and do this project or write this code, which is meaningless to you, right? And soon we get to the realm that intelligence become pretty much like internet. And if you don't have the intelligence on your computer, you probably close your laptop and go and play outside. It's something like that. So first of all, you need to be really good at it, at top of it. And for the computer science people, for the software engineering one, you need to use that as much as you can. Because, these days you hear that AI is replacing the software engineer people. Actually, AI is not replacing anyone. The one that are replacing the other software engineer are the one that know how to use AI so that they improve their performance twice, 3 times, or even 5 times. And then the company can get rid of the low productivity kind of software engineer at the low end of the distribution. So if you don't get to know that, then probably chances are you're going to be that person. And also, if you are using AI for your work, you need to understand how it's being done. The less you understand that, the higher the chance that you're going to be replaced by that AI. So just use it for the understanding of the problem that you have. And then when you get out, then it's going to be hard to really replace you. And in continuation to that, I would suggest that you be, not to be actually a pure kind of, how can I say this? A pure, for example, software engineer, a kind of generic one, because that's going to be really easy to replace. But for example, if you're a performance engineer or if you are a security engineer, which is kind of add-on on top of the software engineering, then for foreseeable future, you are going to be good, especially if you know how to use those tools. So make sure that you have this tool in your toolbox and know how to use it and also understand how the work is being done, not to be replaced later by that technology.
Yeah, and I would like to echo Hamzeh's comments here. Is like with my team right now, we have developers going from like, over 10 years of experience, and they can code with their eyes closed without looking at the keyboard. And then when these LLMs came along, they didn't want to use it. But so what we are seeing as a trend, and what we're doing with our team here, is that we're trying to train everyone on how to use these LLMs as a co-pilot in a way, not talking about Microsoft Copilot, but as a person that's just beside you, that's helping you. Because before coding, a lot of us would say, Google it, go on Stack Overflow, copy and paste, and modify it for you. But using these AI tools, you could skip that Googling, the Stack Overflow, and just use it, apply it directly to your code. And using it blindly doesn't work every single time. So you have to learn how to work with it and not just blindly follow it. And that's a trend that I'm seeing, at least inside software developments. And yeah, that's all I have to say.
All right, I may have a somewhat controversial or hot take. I'm not saying this to on purpose, but people skills. Right? We all talk about all the technologies that we have to learn, large language models, and learning all the technologies that are out there. You're going to go out into the workforce, you're going to be working with people. That's the reality. We're not going to be locked into rooms and just in front of a computer and asking it questions and expecting responses back. So invest in your people skills. Invest in learning how to work with people, how to handle confrontation. Yeah.
Absolutely. That'll be the differentiator again, when all of this automation comes in and you have to kind of differentiate what you do. I'll add just a couple of points again, as there are a lot of electrical engineers in the room again. So I already touched on alternative, semiconductor solutions to solving our AI challenges, but pay attention to quantum as well. So the emergence and the progress that quantum has made in the past few years is not insignificant. And, again, speaking from an IBM perspective, we have a strategy around combining quantum and HPC to solve some really interesting problems, and in fact we have a partnership with AMD on that. Again, we'll combine quantum systems with specialized accelerators and things like that. And so that's a space, an emerging space. There's a lot of niche skill right now. Only the kind of the physicists and the PhDs are into it, but pay attention. Is my advice, and pay attention just in general. Read. Be up to date of what's going on. Those are the things I think that I see that people who do that really succeed. So know all the deals that are happening, who bought who, and who's dealing with who, and just stay kind of on top of it. Read the tech rags. And I think those are some good ideas, and stay connected, of course, which is a given. So.
Thanks. Yeah, I was going to echo the connected point because you might remember I was the chair. I am the chair of IEEE Toronto, so you've heard about people skills. You've heard about staying connected. I'm going to give my unbiased pitch for IEEE because I've been involved in that since I was a grad student, and I can say that building your network is going to help you so much. I mean, I'm probably preaching to the choir. You're here. Congratulations. Applause for yourself for actually coming out tonight and sitting through this and listening to me talk. But you've made the first step, and just keep going with that and develop those connections that are going to help you not only get a job, but enjoy the people that you're working with, because you'll have this network that goes beyond just the office space.
Thank you very much. Okay, with that said, I am going to open the floor to Q&A in 1 minute. In that minute, I want you guys to just line up right here where this tall microphone is. And I want to just ask the panelists if there's anything they want to ask each other before we go into Q&A from the audience. Okay, sounds good. So if you have a question for the panelists, data centers in the cloud, or maybe something about what their work, their company, anything of that nature, please feel free to use this microphone right here. Please feel to be brave as well. We'll have 10 minutes for Q&A. Thank you.
Testing. Great. Thanks for the panel, guys. My name is Michael. I'm a Master's of Science student here at York. I had a thought when you were speaking earlier, Rob, about kind of the changes that have come about from cloud coming in, mostly around how it's changed businesses. They don't have to spend as much upfront on compute and so on, which is great, and it democratizes access to compute for people like students or other organizations that don't have as much money to spend upfront. But obviously it creates other problems, I suppose chief among them being maybe the monopolization of resources. Obviously AWS were the big option when this paradigm was first evolving. We've had others coming out since then, but it's still big companies like Microsoft and Google. Small players aren't really finding a foothold. Do you guys see any solutions to this where, you know, smaller companies, or at least less monopolizing companies have an opportunity to contribute to this paradigm?
I guess I can take that. You see it in business everywhere, right? So you see the big fish eating the little fish, and it doesn't matter what the industry is. I think for the smaller folks that are starting up, try to find a niche. Try to solve a problem that someone isn't already solving today, or be better at it than the next person. It's not necessarily a bad thing to have 5 big players doing, you know, data centers, whatever it happens to be. There still is a place for the little fish. So just find a niche, try to do something better than the next person, I think is kind of my advice. Yeah.
Okay, thank you. Thanks, guys.
Hey everyone, my name is Dhruv and I'm a first year's master's student in electrical engineering. So I wanted to touch on a point you guys made regarding just the, like, emerging technologies. So I just wanted your general thoughts on silicon photonics and how photonic integrated circuits can help out in speeding up the work that's being done in data centers, decreasing power consumption, and so on.
Yeah, I can take that one. That's up the hardware alley. So silicon photonics is something that Alphawave Semi has been involved in for many years, and we see it as the future of what data centers will become. Getting from here to that future, there's still a lot that needs to be sorted out. It's not that easy yet to get all that data from an integrated circuit that's built in silicon into the optical domain and transmitted through fibers. We do it when we eventually get to a bottleneck of needing to send data very, very far away, right? All the long distance, high-speed data network on fiber is going to be there to stay, and that will continue to grow. But moving that optical connection all the way to the chip doesn't happen yet. We still convert it to electrical, and it's those electrical pieces that are heating up the data centers that need all of that cooling applied so that the data centers don't overheat. All of that, the more we can change to optical, we've got a chance to lower the power, but we're still spending a lot of power converting between optical and electrical, which you have to do somewhere, and spreading that out is helpful. So there's a lot of challenges there. There's a lot to be solved. It's going to take many years, but definitely the future is in the direction of optical.
Awesome, thanks.
And I'll just add, our research folks are working on it too, and so I can like point you to kind of some of the projects, the folks down in Albany, New York, but we can connect maybe after.
Thanks, guys.
Hey guys, my name is Basit. I'm a fourth-year computer engineering student at York. So my question is that we've obviously talked about data centers, cloud, and this kind of front-end platform. My question is, as we continue to have more high-performance compute, do you think that demand for people like silicon design engineers and silicon design verification engineers is going to continue to increase, or do you think it's going to stay the same or potentially even decrease?
The silicon side, you mean like the actual circuit design, building the chips?
Yeah,
Yeah.
something like MI350, MI400, yeah.
So I can only see that increasing. I think it's there's a role for AI to play in that domain to help make the work that needs to be done there more efficient. But I think the nonstop parade of silicon, of new silicon that is being created and fabricated in these advanced fabrication facilities is going to increase, and we'll need people that understand what's in the circuits and can participate in those silicon verifications and debug problems, which you're going to continue to find forever.
Do you think we're getting close to like that limit? I think now we're at like 1 or 2 nanometer processors, right?
That I don't know. I hope not, right? For a long time, the industry's been saying, okay, this is it, you guys. We're at some number of millimeters maybe, and we can never go smaller than that. And we just, because there's such a benefit, there's such an economic demand to get to that next level, we're now doing crazy things, building huge machines just to focus light in a wavelength that's tight enough to build these tiny structures on a chip. I think that's just going to continue.
I'd say the industry never sits still. Good enough is never, complacency never works. So industry leaders will constantly be innovating. I don't think we're anywhere near. Now, it could be near what we can do today, but it's planning for the next 5, 10 years. That's happening right now.
Yeah, I'll just add too, like all the research that's being done at the universities, we're discovering all these new things. What we know today may not be what it is 5 or 10 years from now. So continue doing all the research that we're doing at York University here and all that. And then we know, who knows what will the future be.
I'll add one wild card. What's different is the geopolitical factors that are changing things. So that alone, I think, will drive more demand for that kind of work.
Perfect. Thank you, guys.
Hi, my name is Aaron. I'm a second-year computer engineering student. You guys mentioned that for data centers, you guys use a lot of virtual machines. What's the difference between, say, opening like a virtual machine versus running like a Docker image or like a Docker container, since it has less resources?
That's a question for me. So it's a technical question. The difference between a Docker and a virtual machine, usually we call VM as a strong isolation and Docker as a kind of weak isolation. In Docker, usually you have a process, and with the resources that process needs, and you just contain it in a kind of portable container, so you can move it whenever you need. It could be for the sake of performance, could be sake of the failure of this machine, or anything. But virtual machine actually is a kind of virtualization of the whole computing system. Basically, whenever you create a virtual machine, all the applications on top, they have a kind of feeling that they are dealing with a real computer. But in fact, it's a virtual entity that you build on top of that. So the usage of these two are different. When you want to have a strong security and a strong isolation of your workload, usually you rent VMs from the cloud. We call it infrastructure as a service cloud. But when you want to deploy an application that you want to be really agile and you can move it around really fast and you don't need that much of concern in terms of security and isolation, You deploy it using containers, and usually for that, you need a kind of orchestrator. Usually we go with Kubernetes, for example, in order to be able to deploy this software system in terms of these containers. And you have a very good chance of scalability, the one that I explained, the vertical scalability, the horizontal scalability. You can increase, for example, you can add new container to your system less than a second. Just imagine how fast you can response to the demand. Let's say Black Friday, you can just increase and decrease. So these are two types of virtualization for different reasons. And we have both of them active in data centers right now in cloud computing.
Thank you so much.
Sure.
And maybe I'll share, just like somebody explained it to me a long time ago, really simple. Like, so in one case, you're virtualizing a computer, a physical computer. A container, you're virtualizing the operating system, right? So maybe that kind of helps.
Thank you.
And I'll just add one use case that I've seen in cloud gaming. So we do have this one company I cannot name, but they're using Dockers and our GPUs to try to run over 70 instances of games at 720p because they're targeting casual gamers. But however, if you're, say, a major player and say you're doing esports, like maybe a League of Legends tournament, you may want to use a virtual machine for security to ensure that no one's cheating. So there's definitely different use cases between the two, and just comes down to what makes sense to that user and the company that's planning to use it.
Thank you.
Hi, my name is Daniel. I'm second year computer science. My question pertains to the use of generative AI in the hardware industry. Obviously, ChatGPT is very good at generating code that works. I'm curious to know, how is AI increasing the productivity of hardware design?
I can speak from the perspective of the company that I'm at now at Alphawave, and I would say that it's not. And I would say that that's an opportunity for that kind of AI to grow and have a big impact. For a company that is building the most advanced circuits and the most advanced process node that you can, the amount of AI adoption that we've had is, I think, quite small. We're still using tools that run on their own as standalone units and rely on the brain and intuition of the person doing the design work instead of AI. And it's because it's such a kind of niche area, it hasn't been the focus of that AI development yet, but I'm sure it's coming. And it'd be a good thing to be a part of.
Thank you.
Hello, my name is Lavon, and I'm a second year of mechanical engineering. And this is something I would like to hear your opinion on. As the industry pushes towards having more cloud computing, both for gaming, just in general, heavy computing activities, this will eventually evolve into becoming some sort of subscription service. We can already see this with like GeForce Now from NVIDIA, for example. At what point or what things does cloud computing need to have for this to become more economically viable, both for the user and more environmentally friendly than the user just having a powerful native machine rather than connecting to a very powerful server to game or to run a very heavy software?
Yeah, so when I was flying on a plane a few weeks ago, and I couldn't do any cloud streaming or cloud game streaming on it. So there's definitely some use cases where you always would need like a strong network connection to do all that streaming. So there's always the end-to-end AI devices. So as AMD, we have our Ryzen AI PCs that's supposed to be able to do some of these AI workloads locally. So I think what our CEO, Lisa, has said, we need to provide solutions that fits all of the family. So including the data center, end units, everything along the way. So I wouldn't say cloud computing is 100% the future. We still need stuff on our devices, such as Apple, which they advertise as super private. Everything's run locally. So again, it's not always about cloud computing. but looking at all the different use cases and running things, even local language models on your own.
As a kind of generic, actually, answer to that question, usually in terms of computation, we would like to bring the computation as much as close to the user for many reasons, for the latency, for the privacy, for many things. And that's been the history. For example, if I want to give you a really quick cycle on that, starting in 1950, we used to have these mainframes, and people need to go to these mainframes. They were like big in this size of this room. Maybe my IBM colleague actually can tell you more about the exact size of that. Then we came upon the personal computer, which was kind of capable enough to handle the daily task. And then we realized the power of networking. For example, being able to use a resource like in the third floor, the local area network. Then from there, when we realized the capability of networking, we said, why not have a kind of network of network that we call it internet, right? So, and then from there, we have grid computing and then cloud computing. These are like paradigm shifting computation. As you can see, whenever we have the capability in terms of our computing unit, we will bring everything local. But at some point, you need to go back again far like cloud, which is far from you in terms of, if you compare your laptop with cloud, basically your laptop is a keyboard and a monitor. It's pretty much like the mainframe era. And again, we will see the same cycle. For example, with quantum computing, at some point, maybe we get our personal computer capable enough to do whatever we want on our computer without the need to be connected to somewhere far again. But who knows, maybe the workload is going to become heavier and heavier. Again, you need to go back to somewhere in cloud, and again, come back to this personal computer. We might have this cycle a couple of times again. But that's a kind of eternal kind of demand that we want the computation to be close to us for all these good things that it brings about for us.
So what is the driving factor to, because the industry overall seems to be pushing, instead of having the computation actually happen on the user's machine, it seems to be moving towards cloud computing for a lot of things. Like, for example, Onshape versus SolidWorks or Fusion. What is lacking at the user end for this push to be happening so much?
My answer to that would be that for many use cases, you have to actually rely on these resources outside of your power. But as I said, we will try. For example, in case of LLM, right? Right now, the way that we interact with LLMs is pretty much like mainframes. This chatting with LLMs is pretty much like typing in the terminal the commands. So right now, we are in the era of mainframe of LLMs. And then we have been seeing this kind of emergence of personal computer version 2, by which you can run the LLM on your computer. We are not there yet, but we are getting close. It's going to be probably in a couple of years that everybody can actually run and ask and talk to the chat on his computer. Right now, for example, if you want to generate a picture, you need to send your request to somewhere. It's pretty much like mainframes, right? And sometimes you need to wait for 10 minutes to get your picture. For example, if you say, give me the Ghibli version of my picture, it takes 5 minutes. And from what I can tell is that we're going to have the same cycle again with these LLMs. We're going to have the personal computer of LLMs, then probably the interconnection of these LLMs together, which we call it agentic AI, when you have multiple agents that can talk to each other. It probably will be locally first, like local area network. And then when you get these agents to talk to each other on a global scale, then it's going to be the internet of LLMs. And I can think of that maybe with the next time we get into the cloud of LLM, maybe even we have AGI somehow present at that time to have it accessible, kind of intelligence, which is accessible to everyone at your fingerprint. And it's very capable. So that's what we usually call maybe artificial general intelligence, be somehow. We get there. Sorry for the long response.
Thank you very much. Sorry for the long question.
Sure.
Working. Last point, though, but price and money drives a lot of this too, right? So the reason people are using GPUs in the cloud, because it's cheaper to use in the cloud than to have one under your desk, right? Because when it's sitting under your desk and you're not using it, that's the expensive part. But when you're using it in the cloud, then you can share it, and then it brings down the price, right? So money at the end of the day drives a lot of the decisions.
Thank you very much.
Cheaper.
Until they make them cheaper, exactly.
Hello, guys. My name's Richard. I'm a fourth-year computer engineering student. And I just want to ask, as it becomes increasingly cost-prohibitive to shrink process nodes of semiconductors, do you think this will drive the proliferation of ASICs further? Or do you have any other opinion regarding this? ASICs as in application-specific integrated circuits.
Yeah, it's a hardware question. I'm a software guy, and the last hardware course I did was like 20 years ago. So,
Yeah.
I guess I can address this just personally, being from an infrastructure background, specifically in storage. What we've done is we've actually moved some of the processing power from big compute onto the hard drive itself, right? And we're doing it for a couple of reasons. One is, the closer you are to your data, the more performance you get out of it. The other thing is for power and cooling reasons, right? So we can have smaller compute nodes to be able to not consume as much energy. So that's some of the things we're doing, at least from the data side of things. You're just, again, back to the point of moving your bottleneck, right? And the economics piece of it. Where can I do things most efficiently? Businesses are always looking at how do I decrease my cost and how do I increase my revenue, right? So if we can do something on the technology side to be able to address one or the other, again, you're getting a competitive advantage.
Okay.
Are you talking about like FPGAs? Is that what you're talking about?
Could you repeat that?
Are you talking about like FPGAs and those kinds of devices? Is that what you mean? Like,
I believe so, yeah.
So my point, I just wanted to add that alternatives to what we have today will always be interesting, right? And so I one of the reasons we signed this partnership with AMD and HPC was because they, you bought an FPGA company, and different approaches are very important and relevant to kind of what is BAU today. So I think they'll be very relevant and continue to be relevant going forward. So take those courses.
Thank you.
Can I get a round of applause for our panelists, please? Thank you guys so much. I really appreciate it. How are you guys feeling? Can I get one more for the panelists, guys? Come on, let's go. More. Come on. Thank you for those of you who are brave enough to ask questions. I'm sure everyone got some value out of that right just now.